All right, hello everyone. Welcome to my channel. This channel is for educational purposes, and we tend to focus on various theories of everything, all-encompassing theories, or just other contributions from researchers who, in my opinion, if you knew their work, it would benefit you in great ways, but usually their work is so suppressed or obscure that you've never heard of them before. Today is, I think, the 333rd video that we've done on Dewey B. Larson's reciprocal system of theory. And Mr. Larson was an engineer who lived in the US in the 20th century. And around 1930, he had some epiphanies, was kind of working on a scientific problem, and had some epiphanies that kind of let him know that this problem that you're working on has much more far-reaching consequences than you're aware of. And he started to, he answered the call, and he started to dig into these more far-reaching consequences, and he recognized that he had something that was way bigger than what he started with. And it was way more fundamental and of a more greater importance. He spent really 30 years of his life working out these ideas without even documenting anything, but just his wife would say that he would sit on the sofa with a slide rule every night and just like work out these different problems that he was working on. Then finally, in the late 1950s, he put out his two fundamental postulates, and that kind of described, in essence, what he had discovered was the fundamental workings of the universe. And then he took those postulates, and through a process of deduction, he came up with a theoretical universe. How does the universe work? And then from that, he wrote many books on, okay, this is kind of how chemistry works. This is how physics works. This is how astronomy works. These are the rules, and this is, how the rules are demonstrated. These are the different characters or actors in these rules. We've got our periodic table of the elements, and we've got our stars and galaxies, and we've got our atoms and subatoms, and how do they all fit together? And so that's how he ended up writing all these books. He even moved it into some of the social sciences and even the liberal arts. And some of his followers, after Larson died in 1990, some of his followers have continued the work and moved into even more subjects. The basic idea behind Larson's reciprocal system is addressing the fundamental component of the universe. And it is not matter, like the ancient Greeks would have told you. And it's not energy, like some of the relativists might have said. It's not force, which is what Einstein spent the last 20 years of his life looking for, the unified field of uniting all of the fundamental forces. But for Larson, the universe was made out of motion, which is not original. Other people have come up with that. But what made Larson stand apart is that he defined motion in a different way. In Larson's conception, motion was the relationship between space and time. And in this relationship, that is a reciprocal relationship between space and time. Space and time are basically the same thing, except they are reciprocals of one another. They don't exist in and of themselves, they only exist together in motion. Motion is basically a fraction with space or time as the numerator and time or space as the denominator. And it's not just motion the way we think about it. The way that Larson defined motion, he defined it really as what you call a scalar motion. A scalar motion is a motion that has a magnitude, but it has no specific direction. You can think of this in terms of a clock time. Time is always getting later and later and later and later, but in no specific direction. Or you can think about this in terms of a balloon that has a bunch of dots on it. If you blow up the balloon, all of the dots are moving away from each other. And the farther they are away from each other, the faster they move away from each other. And that is basically called clock time and clock space. The progression of time getting later and later and later, or the progression of space getting farther and farther and farther apart. And then in addition to that, there's what you call coordinate space and coordinate time, meaning that time and space are both three-dimensional. They both have XYZ coordinates, or the equivalent of XYZ coordinates. And we are accustomed to think of that in terms of space, but not so much with time. Most of the mainstream scientists see there as just being an arrow of time, the progression of time, and not so much a three-dimensional solid of time. And then space and time also come only in discrete units. There's a minimum unit of time, a minimum unit of space, and if you don't have a full unit, then you really don't have that thing. You have to have a full unit before you have any space or any time. And so Larson's first postulate is basically the universe is made out of motion. Really, the universe is made out of three dimensions of scalar motion in discrete units. And then his second postulate, now if you have exactly 1 unit of space in 1 unit of time, you have the speed of light, which is what Larson calls unit speed. And so unit speed is really the background of this reciprocal universe, this universe of motion. And that makes sense. In a universe of motion, the background or the origin or the 0 point, the reference point, the null point, is already in motion. The legacy scientists measure their motion from 0. Larson measures motion from the speed of light outward in all directions. And so that leads to a lot of wildly differing conclusions, consequences. So for Larson, half of the universe is actually moving faster than the speed of light, which he refers to as the cosmic sector. And that is unknown to legacy science, who believes that the whole universe, the speed limit of the universe is the speed of light. Nothing is moving faster than that. That is Einstein's dictum. But that is ignoring half of the universe, called the cosmic sector. The other half is called the material sector that we're familiar with. But you can extrapolate one to the other. Whatever's going on in the material sector is also going on in the cosmic sector, only to the inverse. And so, for example, in the material sector, you have coordinate space, 3 dimensions of space, and you have clock time. The clock is always getting later and later and later. But in the cosmic sector, you have coordinate time. You have 3 dimensions of time, and you have clock space. Space is always getting farther and farther and farther apart. So that kind of shows you the general reciprocal nature of this relationship. When you cross that boundary, you go into a different, you know, a different sector of the universe. My computer is making a bunch of very funny noises right now. I hope that nothing really happens here. So anyway, we are going over a paper that Larson wrote and presented back in the 70s that is called The Mechanism of the Universe. And in this paper, we started yesterday. Larson kind of goes over your basic aspects of cosmology. How does the universe operate on a grand scale? And he had just gotten done. If you want to, go through the first part of the paper, you watch yesterday's video. But for today, we're looking at the second part. And in the first part, he did talk about how, a lot of times the physicists and even the mathematicians have to overlook observations from astronomy to be able to fit it into their various conceptions of the universe. He's going to be talking about that a lot more here coming up, where he's talking about the different models of the universe, the Big Bang and the steady state theory and the oscillation theory. Those are the three major kinds of cosmological processes that that the universe originated in and still operates under. Okay, we're going to start right here. A similar process of enhancement takes place whenever highly questionable assumptions are subjected to advanced mathematical treatment. By the time the original data have been put through a half dozen esoteric mathematical processes and an answer of some kind has been obtained, it is all too often forgotten that the whole construction rests on nothing but the thin air of an assumption. I am emphasizing these points because the biggest obstacle that stands in the way of arriving at an understanding of the remote origins and features of this universe, is the existence of so many errors and misconceptions in what correctly passes as knowledge. As one American humorist put it some years ago, it isn't what we don't know that hurts us. It's what we do know that ain't so. In addition to the information that we get from the stars individually, the observations of stellar groups, clusters as we call them, provide some further clues as to the nature of the evolutionary processes in which they are participating. Indeed, the clusters have been more informative on the subject of the direction of evolution of the stars than the stars themselves. Here again, however, it is by no means certain how the observational information should be interpreted, and consequently its significance has been open to serious question. When we step up to the next larger aggregates of matter, the galaxies, we again find some similar patterns that shed some light on the cosmological question. This completes the astronomical contribution to the solution of the problem, aside from one new factor that has come to light very recently. But strangely enough, these astronomical observations, which constituted the entire basis for cosmological speculation until a few years ago, are now almost totally disregarded. Current cosmological theories make no attempt to connect the evolution of the contents of the universe, the galaxies, the clusters, the stars, the planets, the independent particles, and the non-material constituents, with the evolution of the universe as a whole. The recent findings on which cosmological attention is now concentrated are those which show that the wavelengths of the radiation received from the distant galaxies are strongly shifted toward the red end of the spectrum. If these red shifts are interpreted as Doppler shifts, the only adequate explanation that is currently available, the distant galaxies are receding from us at extremely high velocities, which increase linearly with the distance. This indicates that the entire universe is undergoing a process of expansion. Obviously, any cosmological theory must provide some kind of an explanation for the expansion, as it is clearly a significant feature of the cosmological pattern. As matters now stand, however, the cosmologists are concentrating their attention almost entirely on this one phenomena, as it were, the whole problem. It would not be too far from the truth to say that the current theories of cosmology are nothing more than theories of the galactic recession. If scientific questions were settled by majority vote, the winner in the cosmological race at the present time would be what is rather irreverently called the Big Bang theory. This theory accounts for the recession by extrapolating the observed rate of recession back to zero and assuming that at the time thus calculated, some 10 or 20 billion years ago, all or most of the matter in the universe was contained in one dense mass, which for some reason exploded and ejected its contents at the high velocities that we now observe. The ultimate fate of the universe on this basis will be a situation in which all activity will cease because the constituents of the universe will be too widely dispersed to interact. A variation of the Big Bang theory assumes that the forces of gravitation will ultimately overcome the outward motion and will initiate a contraction that will terminate when the maximum density is again reached, whereupon a new Big Bang will occur. This oscillating theory visualizes a continual series of such cycles without a beginning or an end. In the steady state theory, the effect of the recession in moving the galaxies apart is offset by the continuous creation of new matter, which forms new galaxies to fill in the vacant spaces resulting from the expansion, so that the universe, while always changing, always remains essentially the same. All of these theories are subject to serious objections. The Big Bang is the least open to specific charges of error or inconsistency, but this is mainly because the theory consists almost entirely of untestable ad hoc assumptions. Of course, this is in itself a serious defect in the theory. The oscillating theory is subject to the same objections as the Big Bang theory, with the additional complication that it requires gravitation to be strong enough to eventually overcome the recession, whereas the indications are that the gravitational force is much too weak. The strongest theoretical objection to the steady state theory comes from those who are unwilling to sacrifice the conservation laws by admitting the continuous creation of matter that this theory requires. The history of the theory has been one of alternating rise and fall as additional evidence has accumulated. At the moment, its fortunes are at a low ebb because of two recent developments of an adverse nature. The first of these comes from investigations of the relation of the number of astronomical radio sources to the distance. On the basis of these radio source counts, it is now believed that the universe was more densely populated some billions of years ago than at present. This, if correct, would rule out the steady state theory. Another item that is currently being given much weight is the discovery of an isotropic is the right word, isotropic background radiation that is more or less consistent with the Big Bang and oscillating theories, but is as yet unexplained by the steady state theory. Neither of these new findings is at all conclusive, so far as the validity of either theory is concerned. The radio source counts are open to serious question, particularly since no one knows with any degree of certainty just what kind of objects are being counted. Likewise, the possibility of an explanation of the background radiation that is consistent with the steady-state theory is by no means excluded. Nor is the explanation of the cosmic background radiation in terms of the Big Bang theory as good as is claimed. It is now conventionally forgotten that the temperature of the background originally predicted by the Big Bang cosmologists was significantly higher than the observed value. In any event, it should be recognized that disproof of one theory is not the equivalent to proof of another. Even if the new observations are accepted at their face value, they contribute nothing toward establishing the validity of the central assertion of the Big Bang theory, the assertion that the recession of the galaxies is due to a primeval explosion. Okay, we're going to stop it there. I'm sorry that my computer is being so loud here. I hope nothing is really wrong with it. But we will take over at this location tomorrow and keep going with this paper, The Mechanism of the Universe. Thanks for tuning in today, and have a nice day.